Traditional CT testing follows a black box approach. The CT is solely assessed through its external behavior without considering what is happening inside. 3 such black box testing methods exist, differing in their comprehensiveness and the effort they involve. Primary current injection using a portable high current source. Secondary voltage injection using a portable variac. Primary nominal current injection using a high current source, a reference CT, a burden simulator, and a bridge. Injecting current on the primary side using a portable high current source and measuring secondary current allows the ratio and wiring of a particular core and tap to be checked. This method is insufficient, particularly for verifying metering CTs, because of limitations in the current amplitude, limited accuracy, and the inability to consider different burden values. Using a variac to inject voltage on the secondary side and measuring the voltage induced on the primary side allows confirmation that the protection or measurement circuit is connected to the correct CT core and tap. As it uses power system frequency, the method's accuracy is limited, as it is directly influenced by external disturbances. In addition, it cannot measure a CT's accuracy at defined current and burden values. In generator, transformer, or bus bar differential protection systems, CTs with knee point voltages of several thousand volts are used. These CTs cannot be tested, since applying more than 4 kV to the CT's secondary winding would damage its insulation. If a CT is to be comprehensively tested in a classical manner, the current bridge method is used. Through a high current source, defined values of primary currents, from fractions to multiples of rated current, are injected into a reference CT and the CT under test, which is connected to a controllable burden box to simulate different load conditions. Via a measurement bridge, the output currents from both CTs are compared in amplitude and phase. With this method, all current and burden value combinations defined by the relevant international standards can be verified, and the CT's compliance can be assessed. This method is costly and laborious, particularly on-site, as heavy components need to be shipped and unwieldy cables are required for the current injection. Even this method reaches its limits where protection CTs designed for high short-circuit currents, high DC components in the fault current, or high primary time constants are involved. Such CTs require thousands of amps for testing them, exceeding the largest current source's maximum output current. Additionally, many of the parameters characterizing a CT's transient behavior, for instance during auto-reclosure cycles, such as secondary time constants or remnants, cannot be determined with classical test benches. CT Analyzer allows the limitations of the various traditional methods to be overcome. It opens the black box through secondary injection with variable frequency and a patented low-voltage, low-frequency method for excitation measurement. It identifies all the parameters of the CT equivalent circuit diagram and thus accurately determines the CT's behavior for protection and metering applications. First, it measures the DC resistance of the CT's secondary winding. Then, knowing the DC winding resistance and the corresponding voltage drop, it measures the excitation curve to determine the magnetic characteristic of the core. CT Analyzer performs the excitation curve measurement with safe low voltages of up to 120 volts. Instead of increasing the voltage further, it reduces the frequency if higher magnetic flux is required. Finally, it measures the turns ratio with variable frequency injection and frequency selective measurements, unaffected by external noise. Based on these measurements, it determines the accuracy data for all defined current and burden value combinations. Using this approach, all types and sizes of CTs can be tested, even exceptional types with primary currents of up to 100 kiloamps or with knee point voltages of up to 30 kV. It can test any CT, including installations that by conventional methods have been difficult or impossible to test so far, such as CTs in transformer bushings or gas-insulated switchgear. CT Analyzer achieves an accuracy of 0.02% for ratios and 1 minute of 1 degree for phase angles, even in the presence of the electromagnetic disturbances common on site, and provides all of the important CT parameters. In addition to testing CTs for 50 or 60 Hz applications, CT Analyzer can also test any CT with a frequency rating from 16 to 400 Hz. CT Analyzer is a universal instrument suitable for measuring the parameters of current transformer types of any age.